Hello. Today we're going to be talking about radiation. We'll be reviewing four classes of radiation. If we have alpha decay, we emit what's known as alpha particles. So in this type of radioactive decay, our nucleus is going to emit a helium nucleus, essentially. It's like a helium atom with no electrons. It's going to have 2 protons and 2 neutrons. So the mass of this particle is 4. Our upper number here is the mass number. And we have an atomic number of 2. This lower number is the number of protons. So 2 protons, 2 neutrons for a total of 4 units of mass. And people sometimes abbreviate alpha particles like this, or use the lowercase Greek letter alpha. We also have beta particles. Beta particles are essentially when our nucleus shoots out electrons. So that's what happens during beta decay. And we sometimes abbreviate these as the lowercase Greek letter beta, or we have our E with a -1 right here and 0. So what we're saying here is the electron has virtually 0 mass, and we actually have an atomic number of -1. This is how we make the math work out. You'll see later. And moving on from there, we have positrons. Those are sort of similar to electrons, but they're actually antimatter electrons. I know it sounds crazy. Antimatter is a real thing. But our element is going to emit an anti-electron from the nucleus. And people sometimes abbreviate this as a beta with a positive sign, or they might have the E for electron and then the positive sign here, and again, 0 mass. Our final type of radiation is what's known as gamma radiation. And so gamma radiation is really similar to X-rays. It's super high energy light. So it's not even a particle, it's just light. And we abbreviate this as the lowercase Greek letter gamma. And it has 0 mass and 0 charge. So we have 0, 0 there. So this table right here summarizes our types of radiation. Don't worry about protons and neutrons. We're going to focus on these 4 types here, alpha through gamma. These are important for medicine, so they're the ones we want to talk about. Unfortunately, each of these has a couple different symbols that people use, so you want to make sure that you learn both symbols for each one of these. And we have our mass for each of these. So the alpha particle has a mass of 4, the other ones have mass of roughly 0, and then we have our charges listed as well. So these types of radiation differ greatly in terms of how much they penetrate. So alpha particles can only travel a few inches through air, and a sheet of paper is actually enough to stop them, or sort of the surface of your skin. They don't penetrate very well. But things that emit alpha radiation can be extremely dangerous if you get them into your body. Beta radiation can penetrate further. It can travel further through air, and it can travel through a few centimeters of tissue. So it's a bit more hazardous. And again, any type of radiation source is extremely hazardous if you take it into your body somehow. And gamma rays are the most penetrating. They can travel very long distances through air and travel very long distances through tissue as well. So I'd like you to now pause the video and please complete question 1 on the activity. Welcome back, everyone. We are now going to talk in more detail about these different types of radiation and also talk about how to balance nuclear equations. That's one of the things you'll be expected to do in this chapter. So let's start out with alpha decay. This occurs when we have a really big nucleus. So any nucleus that has over 83 protons is actually going to be radioactive. And they actually fracture apart because there's so much repulsion between those positively charged protons. And they're going to split into a slightly smaller nucleus as well as a alpha particle. And so if we want to balance our nuclear equation, what we see is that alpha particle has a mass of 4, so we lose 4 units of mass. And it has 2 protons, so we lose 2 protons as we transition. So again, what we see when we balance the nuclear equation is the sum of the masses should be the same before and after, and the sum of the atomic number should be the same before and after. So looking at this simple example here, radon is going to decay to release an alpha particle, and we want to predict what other component will be formed. Well, we know that 86 minus 2 gives us 84 right here, so we'd go to our trusty periodic table. And polonium is actually number 84 on the periodic table. And then to figure out our mass of polonium, which isotope of polonium we form, we're going to take our 222, subtract 4, gives us 218. So these actually are easier in many ways to balance than chemical equations. We just know the atomic numbers on either side must sum up to the same thing, and the mass numbers on either side must sum up to the same thing. So moving on and talking about beta decay, this type of radiation occurs if our element has too many neutrons. And so what actually occurs is a little bit weird. You might not have seen this before, but a neutron actually breaks apart to form both an electron and a proton. And so we actually change what element we have here. So if we start out with carbon right here, atomic number 6, we actually form a new proton with atomic number 7, and we make nitrogen right here. So let's take a look at balancing one of these. So we have our potassium 42, and that is going to decay and release a beta particle. Our mass afterwards is going to be the same, because 42 minus 0 gives us 42. And our atomic number, we take our 19 and then we subtract -1. And remember, if you subtract a negative, it becomes positive, so this becomes 20. And so we end up forming calcium. You just go to the periodic table and look at what number 20 is. So again, 42 plus 0 equals this 42 over here. 20 plus -1 equals 19. They have to sum up to the same thing before and after. Now let's go on to talk about positron decay. So when we emit positrons, what happens is we actually have an atom with too many protons, and one of our protons is going to fracture into both a neutron and a positron. And so what we see is that our mass number will remain the same because the positron has essentially 0 mass. So we start out with 49, we end up with 49 afterwards. But our atomic number is actually going to decrease because we're losing a proton as it becomes a neutron. So we're going to go from 25 down to 24 when we eject that positron. And so we figure out that we have chromium here because we just simply go to the periodic table and we see that chromium has atomic number 24. Our last type of radiation is actually the simplest type, and it's gamma radiation. So what happens is our nucleus is going to rearrange. This M right here means it's essentially kind of a unstable form of this isotope of technetium. And so what's going to happen is that's going to decay into a more stable form, and it actually emits light. And because the gamma ray has 0 mass and 0 charge, our mass number and our atomic number stay exactly the same. So easy here. Mass number and atomic number are the same before and after gamma radiation release. Alright, so here we just summarize our different types of radiation. It talks about what type of change occur. For alpha radiation, our mass number decreases by 4, our atomic number by 2. And for beta radiation, we have the same mass number, but our atomic number increases by 1. For positron radiation, we have the same mass number, but our atomic number decreases by 1. And then finally, for gamma radiation, our mass number and atomic number stay the same. So I'd like you to now pause the video and please complete question number 2. Welcome back, everyone. Let's go to our last topic, which is half-life. And when a radioactive material decays, what we see is it has a set interval of time over which the material will sort of be divided in half, the amount of it that remains. And unsurprisingly, people refer to this as a half-life. So this particular isotope of iodine has a half-life of 8 days, though other isotopes will have longer or shorter half-lives. And what we see is after 8 days, we go from 20 milligrams down to 10 milligrams, so we have half left. And if we go another 8 days, from 8 to 16, we have half that again, so now we're down to, it'd be 5 milligrams. And then if we go another 8 days, we'd be down to half of that, so 2.5, and so on and so forth. So we have this type of curve right here as this thing decays, where there's this set amount of time that we keep having our amount over. And so if we look right here, how do we do some calculations? So if we want to calculate how much we'll have left, we can use these equations right here. So n represents our number of half-lives that have passed. So to find the number of half-lives that have passed, we're going to take our time, and we're going to divide it by the length of our half-life. So let's say that our time is something like 12 days, and our half-life is 8 days. We divide 12 by 8 to find out how many half-lives have passed. We're now going to use n in the equation below. So we're going to take our amount of we're going to find our amount of material remaining by taking the initial amount we started with times 1/2 to the n power. So again, this is our amount of material we start with. This is going to be our amount at whatever given time, and we multiply our initial amount times 1/2 to the n power, where n is time divided by length of half-lives. So I'd like you to take a shot at questions 3 and 4. If you struggle with these calculations or anything else from this activity, please go ahead and post in the discussion board. Thank you. Bye.